in this problem, we are asked to determine a suitable oxidizing agent to oxidize lactate into pyruvate. And we are given two options, either oxaloacetate, which can be reduced into malate with a reduction potential of minus 0.166 volts, or acetaldehyde, which is reduced into ethanol with the potential of minus 0.197. So for any oxidation reduction reaction, we will need to have both the compound that gets oxidized and the compound that oxidizes this compound and gets reduced, right? So I can write down a reaction like that. So I'll shorten lactate to L, so lactate plus the oxidizing agent, which we need to determine. And in the course of reaction, lactate is going to be oxidized into pyruvate, and the oxidizing agent is going to be reduced, right, into reducing agent. And correspondingly, it can be, for oxidizing agent, it can be either oxaloacetate or acetaldehyde, and the reducing agent, the corresponding reducing agent is either malate or ethanol. So for this reaction, we can determine the change in the reduction potential, right? Again, it's important to remember that the tabulated values are given for the reduction potential. So all those half reactions should be written in the form as they are written for those two compounds for the reduction reaction, right? When the oxidizing agent accepts those electrons to become reduced. It means that for this half reaction, this reduction potential needs to be flipped. The sign for this reduction potential needs to be flipped. So we can simply say that we can use the reduction potential for this oxidizing agent, right? And depending on which we choose, it will be either oxaloacetate or acetaldehyde, minus the reduction potential for correspondingly the oxidized form of the compound that we are oxidizing, right? In this case, it will be for pyruvate, this one. And we know for the reaction, for the oxidation reduction reaction to be thermodynamically favored, the change in the reduction potential should be positive. And so we know the value for the reduction potential of pyruvate. So we can rearrange with inequality shown and determine that a suitable oxidizing agent should have the reduction potential which is higher than the reduction potential for pyruvate, so that the overall change in the reduction potential is positive. And the value for the oxidizing agent that is higher than that for the reduction potential of pyruvate will be this one, right? Higher, we mean less negative, right? And we can double check, sorry. So if we plug the values and we just calculate the reduction potential difference for the reaction between lactate and oxaloacetate, we will use the value for the reduction potential of oxaloacetate first, and then subtract the value for the reduction potential of pyruvate, which is the oxidized form of lactate, which is the product of this reaction, right? And this value will be very small, but positive, right? 0.019 volts, if I correctly did the math. So this value is positive, right? So if we are talking about oxaloacetate as an oxidizing agent. And if we want to double check for acetaldehyde, it would be minus 0.197 minus 0.185, and this will be minus 0.012, right? 12 volts. So negative value. And we remember that negative difference in reduction potential translates to a positive delta G value, because we know the formula that delta G for reaction can be determined from the difference in reduction potential as minus n, which is the number of electrons transferred, F, by the change in reduction potential. So if it's negative, it means that the difference in reduction potential is positive. So our choice for the oxidizing agent that would be able to oxidize lactate into pyruvate would be oxaloacetate.